Hello everyone, I'm Ryan Keeley, I'm a lecturer at UC Irvine. So in this talk I will discuss various investigations into the DESI preference for evolving dark energy. I do these investigations using my transitional dark energy model and answer questions like, does the preference for evolving dark energy depend upon the CPL parameterization? And no, it doesn't. And I also answer questions like, what is happening with the data that gives rise to the preference? And how can we test this preference on future datasets? For example, using the growth-weighted structure. So the point is to build intuition about what features a physical model would need to have in order to fit the data. So in general, I'm interested in testing the Lambda CDM model. I try to pull it apart and see where it breaks. The Lambda CDM model is pretty remarkable in that it can explain a bunch of pretty novel physics with just 6 parameters, from inflation to recombination, the growth of large-scale structure, and the late-time acceleration of the universe. It's pretty non-trivial that these 6 parameters fit these diverse datasets at all. For instance, if Lambda CDM eventually gets overthrown, then why was it close to fitting these datasets at all? And the intuitive answer is that whatever finally replaces Lambda CDM would have to be categorically close to it. So there are a few different ways to pull out Lambda CDM and its assumed GR, but today I'll focus on testing the lambda part by measuring low redshift distances. So the DESI preference for evolving dark energy comes in the form of a CPL or W0 model. So these sort of DE models or parameterizations do not really address what dark energy is on a fundamental level, but merely parameterize how it evolves with redshift via its equation of state parameter W of z. The CPL model parameterizes W of z with this form as shown here. So the region of this W0 WA parameter space that's preferred by DESI is interesting since W0 is greater than -1 and WA is less than 0, such that the dark energy starts at a high redshift in a phantom regime, that is where the dark energy equation of state is less than -1 and thus increasing with time, and then it crosses into a quintessent regime where the dark energy equation of state is greater than -1 and thus decreases in time. So the total significance of this preference ranges from 2.8 to 4.2 sigma, depending on the supernova compilation. And so the first thing I seek to answer is simple. So does the preference for evolving dark energy depend upon parameterization? And so I take the CMB plus BAO plus supernova likelihoods and try to fit my TDE model to them. So this TDE parameterization allows for rapid changes in the equation of state, but basically also changes like that in CPL. And so TDE is also preferred over Lambda CDM, indicating that the preference for evolving dark energy over Lambda CDM is not an artifact of CPL, essentially corroborating the findings of the DESI collaboration. So what's actually shown here are samples of WZ drawn from the posterior of the TDE fit to the CMB plus DESI plus DES datasets. Each of the samples are color-coded by how well they fit the data. Yellow corresponds to the best fit, and blue corresponds to a 2 sigma limit. You can see how the best fit prefers W of z functions with rapid transitions around redshift of 0.5, but includes W of z functions with more gradual CPL-like functions, and also functions that will remain quintessent up to much higher redshift. Point being, again, is that this is not an artifact of CPL, that these datasets prefer some sort of evolving dark energy. So speaking of 2 sigma, I'm going to now explain how I calculate 2 sigma. So starting from the beginning, common ways Bayesians calculate 2 sigma is to plot the joint 2D posterior for the various combinations of parameters in a triangle plot and draw a line around the contour that contains 95% of the points from the chains in that 2D space. For example, for the W0 WA parameters, then if the -1, 0, i.e. the Lambda CDM point, is outside of the 95% contour, then Lambda CDM is rejected at greater than 2 sigma. This, of course, leads to projection effects, however. So what you really want is a contour that contains 95% of the full n-dimensional space, not the 2D projections. To be more specific, we want the likelihood or chi-squared contour that encloses 95% of the volume of the posterior. And since the chi-squared value only increases the further out you go, away from the best fit, that chi-squared value is unique for each contour. Thus finding the confidence level in terms of parameters can be rewritten, as it were, in terms of the confidence level in terms of the chi-squared values. And incidentally, this is the basic insight of nested sampling. So in this distribution, the chi-squared value at which 95% of the samples are better fit than it, then that is the chi-squared value of the 2 sigma confidence interval. And if Lambda CDM has a worse chi-squared than this, then Lambda CDM is outside the 2 sigma confidence level and is thus rejected at the 2 sigma confidence level. Incidentally, this is how I get the 3.4 sigma value that I've mentioned earlier. And basically that's what's plotted here, showing that lambda CDM is outside the 3-point sum sigma confidence level, and also showing where the 2 sigma confidence level is in order to determine the color coding in the previous plots. Furthermore, just as an aside, you basically can't solve these projection effects just by calculating profile likelihoods. You're still not really solving anything about projection when going down from ND to 2D or 1D with profile likelihoods. So now I want to discuss kind of the actual important parts of this talk, basically how to test the preference for evolving dark energy on future data sets, namely the growth of structure. So to explain, I've basically reproduced the growth equation here. As you can see, the growth rate is dependent on the expansion rate, and so any evolving dark energy model would necessarily have a different growth rate, even in pure general relativity, or even if dark energy doesn't cluster. So for intuition, when the expansion rate is greater than that in Planck Lambda CDM, say around 0.5, the growth rate calculated assuming GR is suppressed. Relative to the Planck Lambda CDM model, and it rebounds as the expansion rate differences between the models become smaller closer to the present time. The resulting flattening of the F sigma 8 curve compared to the Lambda CDM model could be an independent signature of the temporal evolution of dark energy. So what we're showing are the predicted distribution of F sigma 8 values drawn from the TDE posterior fit to the CMB plus BEO supernova and supernova datasets. Compared to the Planck Lambda CDM curve in black, at redshifts above z of 1, the best fit TDE parameters predict basically the same F sigma 8 values, but at z less than 1, the curve has a different shape. So between redshifts of 0.25 and 0.75, the dark energy density, and thus h of z, is higher in evolving dark energy models than in Planck Lambda CDM, and this decreases the growth rate of structure at those redshifts, as seen in the equation represented here. By redshift 0, the dark energy density and hence the expansion rate of the TDE parameterization is smaller than in Planck Lambda CDM, causing the growth in the TDE parameterization to increase relatively. The TDE on the whole, this makes F sigma 8 flatter with respect to the best fit Planck model. The DESI white paper forecasts around 3% errors on F sigma 8 over multiple redshift bins, basically in the redshift range where TDE diverges from Planck Lambda CDM. These model prediction differences are at the 5% level. Therefore, importantly, this flattening of the F sigma 8 curve could be detectable given, say, the final result of DESI F sigma 8 data. So incidentally, this evolving dark energy model is not a solution to the H0 or S8 tensions. Basically, the DESI data introduce their own omega matter tension, which is resolved by, say, evolving dark energy. So now I want to build some intuition about why these combinations of CMB plus BEO plus supernova give rise to the preference together. So part of the intuition building is to answer the question, why does WCDM fit to CMB plus DESI plus supernova datasets? Why does this kind of model prefer W is equal to -1? And does this mean that the W0WA CDM fit to these datasets is a coincidence? So starting with the CMB, recall that if a cosmology constrained by the CMB, then it needs to give the right angular size subtended by the sound horizon, basically dA at z star. Assuming no change to the sound horizon at last scattering, this is a constraint on dA of z star. This can basically produce a mirage of W equal -1 dark energy while having a strongly evolving dark energy subject to certain constraints. So the mirage that I'm talking about requires that in order to satisfy the distance to the surface of last scattering for models where W of z equals 0 is greater than -1, then W of z must be less than -1 at higher redshifts, and vice versa. So the CMB constraint alone selects for a family of WZ functions that have this feature. However, the supernova datasets show a preference specifically for W at z equals 0 to be greater than -1, and thus automatically that the equation of state for dark energy at z greater than 1 has to be less than -1. So basically, if it has to be quintessent at z equals 0, then it must be phantom at higher redshifts. In summary, the CMB alone tells us that the WCDM kind of model alone is not flexible enough to allow for reasonable dark energy models. So here we show in gray curves that represent the values of W at z equals 0 and W at z equals 1 for different values of H0. Basically, each of these curves satisfy the best fit Planck parameters for the background expansion, namely things like, say, dA of z star and H at z star. So this demonstrates that the impact of the CMB and how the mirage appears. Further, when h0 is closest to the Planck Lambda CDM value 67.36, this calculation yields the curve in black that and specifically that w at z equals 0 and w at z equals 1. Basically, each of these values would most closely mimic and hence mimic the mirage of Lambda CDM when you don't include high-quality, low redshift distance measurements, like in supernova or BAO. So further, by not allowing WA to vary, or i.e. by fixing it to zero, one artificially finds that W naught is equal to -1. This seems to be a coincidence, and the fact that the constant W of Z model prefers W is equal to -1 does not by itself illuminate the question of whether CMB plus DESI plus supernova, whether that preference for evolving dark energy is robust. So we see that the CMB alone allows for entire families of W of Z equals 0 and W z equals 1 curves. We also see the posteriors for W of Z equals 0 and W z equals 1 for different combinations of likelihoods, basically different posteriors in terms of those, in terms of essentially the value for W of Z at different redshifts. So the preference for evolving dark energy arises from specifically high quality low redshift measurements like with the BAO and supernova datasets. Basically, to see this, notice that the supernova datasets do prefer that W at z equals 0 is greater than -1. The BAO dataset calibrated by the CMB sound horizon prefers h0 values between 70 and 65, and the CMB's angular diameter distance sets the evolution of then dW over dA. So the constant WZ models still want h0 of around 67.7, and thus the CMB constraint basically puts us along the black line that intersects close to W is equals 0 and W is equals 1 is equal to negative 1, -1 in the space. And so if by assumption that WA is forced to be 0, then basically the constant of WZ model, then the CMB alone would want W naught to be around -1. So it's worth noting that in this regard, that DESI and supernova contours basically, because they have different slopes in this space and neither follows the CMB curves exactly, this demonstrates the fact that they're basically adding independent information about dark energy changing with time. So moving on. So basically what are shown here are specifically residuals of the BAO data points divided by their errors. And the point of making this kind of plot is to reveal that there's actually no significant outliers in the DESI data around evolving dark energy best fits. Indeed, if you were to actually ignore the most discrepant points in the Lambda CDM fit, then the remaining points are too good of a fit. They don't scatter as much as the error bars on the data points say they should. Basically, you're over constraining your model. And the same happens actually with supernova dataset. And interestingly, both the BAO and supernova data shift, both of these residuals shift at the same redshifts when moving from, say, Lambda CDM to transitional dark energy. And so this indicates that the data are basically telling consistent stories. So the main objection to DESI preference tends to actually be more purely theoretical. So where the DESI W0WA model that best fits the data, where it crosses the line, so where the DESI W0WA model that best fits the data crosses the phantom line, such parameterization is hard to replicate with an actual model derived from a Lagrangian, as it were. So for instance, in GR, a canonical scalar field must have W's greater than -1. Basically, it has to stay quintessent. If you instead modify the kinetic structure of the scalar fields, like in k-essence models, one can get W is less than -1. You can get phantoms with k-essence. Though those kind of k-essence models can generically have ghosts, runaway behavior associated with unbounded Hamiltonians, like negative energy states. So one solution to this W is equal to to the crossing at W is equal to -1 is basically to have multiple fields, say one k-essence and one quintessence. But this kind of model can basically only cross from above. Basically, it would have to start out in quintessent at high redshift, and then and only at lower redshift could the k-essence field growing as a function of time. Only if that field only dominates at, say, lower redshift, that would indicate basically a crossing of the phantom line basically only from above. So basically, thus, any sort of physical mechanism to cross W is equal to -1, you can basically do this with multiple instances of, say, k-essence fields and quintessent fields. But perhaps simpler is basically that you would need basically you would basically need instead basically beyond GR models, like say Horndeski models. It is so essentially these G3, G4, G5 terms can allow for the possibility to cross -1 in the way the data wants, though you basically have to go basically beyond Horndeski in order to further satisfy that, say, the speed of tensors is 1. So in any case, it's basically reasonable to test models that basically have an equation of state that's strictly greater than 1 to represent the simplest case of a theoretical model of evolving dark energy. So one kind of parameterization of this kind of fact is some sort of some Pate model, Pate W model, basically represented here. So it is the case that this kind of Pate W model is preferred over the Lambda CDM model given the CMB, supernova, and DESI datasets, but the CPL model is basically preferred essentially even better than the Pate W model. The question is then, how significant is the preference for CPL over Pate W, given that it still has a better likelihood than Pate W? So the strategy to answer this question is basically to answer the question if the true, so by basically setting up a Monte Carlo kind of problem where we're trying to answer the question is if the true model is a thawing quintessence model, i.e. the real data are generated from a thawing quintessence model, then what is the chance that we would find the CPL with a phantom crossing? What is the chance that we would find that model fits our mock data better than the true model just by chance? And incidentally, this is the standard definition of, say, significance. So the way to answer this question is to just basically just do the simulations, basically a Monte Carlo approach. So basically in this figure, we generate 10,000 realizations of mock data where the fiducial model is the best fit Pate W model to the real data, and then we basically add noise based on the real covariance matrix of the real datasets. We then fit both the Pate W model and the CPM model to each mock data and find the parameters that basically finding the parameters that minimize the chi-squared for each model. We then plot the distribution of the differences in chi-squareds between these two best fit mock datasets. We then see where the real difference in chi-squared lies in this distribution. And basically at around only 3% of the time do the realizations have a stronger preference for CPL over Pate W than in the real data. And so then so basically we say that the preference for CPL over Pate W is at the level of a bit over 2 sigma. So one final note about projection effects, as I've written here. As I've written here, I'm demonstrating that 95% of the 95% contour of a 2D projection of a chain is not the same as the 2D shadow, as it were, of the 95% contour of an n-dimensional posterior. So what's shown here are basically results of a CPL fit to a CMB, BAO, and supernova likelihoods. The blue in the bottom plot is the 95% contour of the chain projected onto the W0W space, basically the typical kind of posterior that you might get from doing a standard kind of analysis. So the black lines are basically something specifically different. So basically they're basically represent if you were to draw a line around all the points that have a chi-squared value better than the chi-squared corresponding to the 95% contour of the full ND posterior. So basically, if you take the chi-squared value that would correspond to 95% of the volume as calculated in the top plots, basically the black lines in the bottom plots indicate all of the W0WA parameters basically that do satisfy that at least once. Ultimately, the thing that I'm trying to convince everyone of is that the common ways that people project n-dimensional posteriors down to 2-dimensionals, these schemes typically underestimate volumes of posteriors, and correspondingly, they necessarily overestimate significances. Okay, thank you for your time, and I'll leave with the summary here.